All right, let's dive right in. Today, we're talking about a pretty huge breakthrough that could totally change how we build AI. What if I told you we could make AI training way faster and a whole lot cheaper just by using incredibly tiny numbers? I know, it sounds a little like sci-fi, but some amazing research from NVIDIA is making it happen. So this right here is really the billion-dollar question for the entire AI industry. We all know that bigger AI models tend to be smarter models, but that size comes at a crazy cost. We're talking energy, time, and just raw computing power. So how do we keep pushing forward without the cost just going through the roof? And this really sets up the central conflict, doesn't it? On one hand, you have this relentless race to build bigger, more powerful AI. But on the other hand, you have the cold, hard reality of what that actually costs. Building the next big thing in AI isn't just a coding problem anymore. It's a massive resource problem. And to give you a sense of the scale here, researchers measure this stuff in flops. In training, a top-of-the-line AI model today takes hundreds of yottaflops. That's a 1 with 26 zeros after it. I mean, just try to wrap your head around that. It's an absolutely astronomical number, and it represents a staggering amount of resources. This is exactly why finding ways to be more efficient isn't just some nice little bonus feature. It's the critical roadblock we have to get past to unlock the next generation of AI. Seriously, without this, progress could slow to a crawl. So how do we get more efficient? Well, one of the most exciting answers is to actually change the fundamental language computers use to learn, the numbers themselves. The basic idea is pretty simple. What if we could use smaller, simpler numbers to get the same job done? Okay, to really get this, we need to talk about something called floating point precision. Don't worry, it's not as complex as it sounds. Think of it like this. A 32-bit or 8-bit number is like drawing with a super sharp pencil. You get incredible detail and precision, but it takes forever to fill a big page. A 4-bit number? That's like using a thick crayon. You can color in a huge area really, really fast, but you're going to lose all those fine details. Right now, the industry standard is what's called FP8, or 8-bit. That's our sharp pencil. It's a pretty good compromise between detail and speed. But the real prize, the goal everyone is shooting for, is to get to FP4, our thick crayon. If we could make that work, we'd get this unbelievable boost in speed and use way less memory. It would be a total game changer for training AI. But here's the catch, and it's a big one. You can't just flip a switch and start using these smaller, simpler crayon numbers. When you drop the precision that much, the whole training process, which is incredibly delicate, just starts to fall apart. The model becomes really unstable. And that instability causes a ton of other issues. The whole training run can just collapse. The model might not even learn anything at all. That's what researchers call poor convergence. It's a nightmare to implement, and these problems get exponentially worse the bigger your model gets. And this is where the big breakthrough happens. The researchers at NVIDIA didn't just find one magic fix. Instead, they came up with this really clever toolkit, a bunch of different techniques that all work together to solve this stability problem. And they called their new format NVFP4. So, their recipe has 4 main ingredients. First, they use a cool math trick to handle outliers. Those are just extreme numbers that can mess up all the calculations. Second, they figured out a smarter way to simplify the numbers that keeps everything consistent. Third, they use a better method for rounding numbers so that tiny errors don't pile up and skew the results. And finally, and this is super smart, they keep a few really critical parts of the AI in high precision. It's kind of like putting in a few steel beams to make sure the whole building stays standing. Okay, so the theory sounds great on paper, right? A clever recipe to make 4-bit training work. But the real question is, does it actually hold up in the real world? Well, the researchers put it to the ultimate test. And they didn't just play around with some small toy model. Nope, they went straight for the big leagues and trained a massive 12 billion parameter language model. This was a serious, large-scale experiment. And they trained it on an absolutely colossal data set, 10 trillion tokens of text. This makes sure that the test is super rigorous and that it actually reflects the kind of heavy lifting required to build a cutting-edge AI. In fact, and this is a quote straight from their paper, this was the longest publicly documented training run in 4-bit precision to date. So they weren't just testing a theory, they were actively pushing the boundaries of what everyone thought was even possible. And here we go. This is the moment of truth. On the left, you've got the accuracy of a model trained with a regular old industry standard FB8. And on the right, The model trained with their super efficient NVFP4. Just look at that. The bars are practically identical. They got the same level of performance, but with all the incredible speed and memory savings of 4-bit. They actually did it. So what does this all mean? Let's zoom out for a second and look at the big picture, because the ripple effects from this experiment are going to be huge for the entire field of AI. At the end of the day, what this research proves is that stable, accurate training with these tiny 4-bit numbers isn't just some fantasy on a whiteboard anymore. It's a practical reality. This isn't a small step. It's a giant leap forward. And why should you care? Well, it means we can develop new AI models way faster. It means that cutting-edge AI research becomes more accessible to people outside of giant corporations. It paves the way for even more powerful and amazing models down the road. And, maybe just as important, it could seriously reduce the huge energy footprint of AI development. What this breakthrough really does is tear down a massive barrier to progress in AI. By making training so much more efficient, it frees up all these resources and all this brain power to aim at the next big problem. And that leaves us with one final, really exciting question to ponder. Now that we've unlocked this new power, what great challenge will AI solve next?